Back. Lesson 13, Integer Representations and Algorithms. Introduction. Integers can be expressed using any integer greater than 1 as a base. You see, we think of numbers in base 10 because that's natural to us. That's what we learned from childhood. But given any integer greater than 1, you can use it as a base. So here is the theorem, main theorem. Let b be an integer greater than 1. Then if n is a positive integer, it can be expressed uniquely in the form n equals ak b to the power k plus ak minus 1 b to the power k minus 1, so on. a1 b to the first power plus a sub 0 b to the 0th power. Where k is a non-negative integer, a0 through ak, these coefficients, are non-negative integers less than b, and ak, that's the leading coefficient, is non-zero. What does this mean? Let's see a few examples. First, an algorithm for the construction of base b expansion. So this sum written in this fashion is called base b expansion. So base b represents the fact that I'm using powers of b. Take your n, divide by b, you get a quotient, call it q0, and a remainder, call it a0, a0. This a0 is here. So this a0 being remainder is less than b and is non-negative. Take your quotient, that is your new dividend. Divided by b, you get a new quotient and a new remainder. That remainder is again between 0 and b. That's that. Keep going until you get quotient 0. The process terminates when we obtain a quotient equal to 0. The base b expansion then is, you start from the right hand most. That is, the very first remainder goes on the right. Next remainder goes to the left of your original remainder, and keep going. So you write from right hand side onwards. Okay. So procedure, base b expansion. So this is a pseudocode. Name of the procedure is base b expansion. What are the inputs? N, the integer you wish to expand, and b, thus the base. They are both positive integers with the base being greater than 1. Start with q to be n. So that's your quotient, right? And k to be 0. So that you are going to now find the very first remainder. While the quotient is non-zero, you divide the quotient by b. The remainder you get is called ak. So it's assigned to the variable ak. And q then gets updated by the quotient when older q is divided by p. And then you update your index k. You keep doing this until q becomes 0 when you stop. And then write down your remainders starting from the right hand side, a0, a1, so on. Because this represents base b expansion of n. Here is a table of decimal numbers 0 through 15 in hexadecimal representation. Hexadecimal means base 16. Octal representation, that's base 8. Binary representation, that is base 2. Notice 16 is interesting because you are allowed digits 0 through f. What is f? What is a? 9 you understand as a digit. 10 is a. 11 is b. 12 is c. 13 is d. 14 is e. And 15 is f. Octal representation. Octal means base 8. So you are allowed digits until 7, and 8 becomes 1, 0, 9 becomes 1, 1, and so on. Binary, you are allowed, so binary is base 2. So you are allowed digits 0 and 1, and 2 becomes 1, 0, 3 becomes 1, 1, and so on. Notice In base 2, you are allowed only digits 0, 1. In base 8, you are allowed digits until 0 to 7. Base 16, 0 through F. Decimal, 0 through 9. Let's study an example of 14, right? So I want to see how they got these values here for 14, right? So 14, let's write it in base 8 using our pseudocode. 14 is your initial quotient. Divide by 8. 8 goes in 14 once. That's your new quotient. Remainder 6. So that 6 is placed here. Use that quotient, divide by 8. 8 is bigger, so new quotient is 0, remainder is 1. That 1 goes here, quotient is 0, so that ends your octal representation, 1 6 in base 8. So 14 in base 8 is 1 6. Likewise, let's go to base 2. Take 14, that's your initial dividend, divide by 2. Quotient is 0, remainder, quotient is 7, remainder is 0. That 0 is here. Take the quotient, that becomes your new dividend, divide by 2. Quotient is 3, remainder is 1. That 1 comes here. Take the quotient, becomes the new dividend, divide by 2. Quotient is 1, remainder is 1. That is that 1 here. Take the quotient, becomes the new dividend, divide by 2. 2 is bigger, so 2 times 0 is 0. 1 remainder. So that's your 1. Quotient is 0, so we stop our procedure and binary representation is given here. 1 1 1 0. All right. Now let's try this example. 253 in base 2, base 8, base 16 and base 10. Let's look at base 2. Take 253, that's your dividend, divide by 2. Quotient is 126, remainder 1. So write that 1 here. Take your quotient, that's your new dividend, divide by 2. Quotient is 61, remainder 0. That 0 comes here. Take your quotient, divide by 2. This is your new quotient, that's your new remainder. That remainder comes here. Take your quotient, that's your new dividend, divide by 2. New quotient, new remainder. 15 is your new dividend, divide by 2. Quotient is 7, remainder 1. Take 7, divide by 2. Quotient is 3, remainder 1. Take your 3, divide by 2. Quotient is 1, remainder 1. Take your 1, divide by 2. 1 is smaller, so quotient is 0, remainder is 1. Quotient is 0, your representation ends. Binary representation, remember all the remainders are written from right hand side moving left. So that's base 2 representation of 253. Let's look at base 8 representation. Take your 253, divide by 8. Quotient is 31, remainder 5. Take 31, divide by 8. Quotient is 3, remainder 7. Take your 3, divide by 8. 8 is bigger. Quotient is 0, remainder 3. Quotient is 0. Our octal representation ends. So 253 is 375 in base 8. Notice the digits are less than 8 always, okay? 16. Your allowed digits are 0 through F. Remember that? Because your allowed digits less than 16. Starting from 0 until 15. So that's a 10, 11, 12, 13, 14, 15. Take your 253, divide by 16. Quotient is 15. Remainder is 13. 13 is D. Take your quotient, That's your new dividend divided by 16. 15 is smaller than 16. Quotient is 0, remainder is 15. 15 is F. Quotient is 0, you stop. So D first on the right hand side, then F. FD base 16. FD base 16. That is your representation of 253 in base 16. What about decimal expansion? Well, it just means 253 as we understand. 200 plus 50 plus 3. That's what this is. That's what these expansions are. Okay, we'll continue in our next video.